Welcome back. So we'll continue the discussion on this equation of the flapping blade motion under force condition. So here we are considering the yaw effect and the wind effect, where we are going to look at the linearized lift force. And linearized lift force we are going to consider because it's a simplified system. Essentially, we would be ignoring the drag force, assuming that doesn't have too much of impact on the system. Now we can find out this uh, lift force uh, per unit length, that is L bar, can be written as half of rho C CL alpha UP UT minus theta P UT square. So here is the chord length, CL alpha is the slope of the lift curve. So UP is the wind velocity, perpendicular to the rotor plane. UT is the wind velocity tangential to the blade element. Theta P is pitch angle. Okay. So now the equations for wind velocity component, which take into account axial flow, flap rate. So the equations for wind velocity components that take into account axial flow, flap rate, yaw rate, yaw error, and wind shear. So obviously the details of these individual components can be derived later on. So what we have is UP is U into 1 minus A minus R beta dot V0B plus UR sin psi minus UR by R K mu is cos psi, and UT equals to omega R minus V0 plus Q D your cos psi. U is the free stream velocity, A is axial induction factor, V naught is crosswind velocity, which is due to your error. Mm, we have K mu s, which is wind shear coefficient. Mm, Then you have d yaw, which is the distance from rotor plane to your axis. So this is what we are going to get as the wind velocity components. And while getting those wind velocity components, which will take into account this axial flow, flap rate, yaw error, wind shear, everything, and you would get this where U is the free stream velocity, is the axial induction factor, V naught is the crosswind velocity, Knu is wind shear coefficient, dE is the distance from the rotor plane to your axis. So all this. So considering individually all these expression, we'll finally get this. So now we will derive this one by one. So to do this, we need to have a velocity diagram, um, which is important. So let us have that. Let's say we kind of draw that is there. Mm, So this is omega r is ut. This is u1 minus a is up. This is alpha theta p. So, and this one is ur. So here what you have in this um, A is axial induction factor, uh, R is radial distance from axis of rotation, ur is relative wind velocity, up is perpendicular or axial component of wind velocity, ut is tangential component of wind velocity, and omega is angular velocity. So here we will consider the steady wind. Start with a steady wind, then subsequently we will consider the yaw error, yaw motion, and all these things. So here in this particular figure, the P is relative wind angle. So that is essentially tan inverse UP by UT. Alpha is angle of attack. Okay. UR is UP square plus UT square. Okay. So these are all the associated information that one would need to now to derive the thing. We'll have some, these are all nomenclature or information that is required. So the assumption A, rotational speed is high relative to the wind speed. That is, UT is much higher than UP. B, the lift curve is linear and passes through zero. So CL equals to CL alpha into alpha, where CL alpha is the slope of lift curve. The angle of attack alpha is small. Okay. Small angle assumption may be used as appropriate. No wake rotation, and then the blade has a constant chord, no twist. Although the model can be extended to include a non-constant chord and blade twist. So this is what we need the velocity diagram to start with. Where we have this axial component UP, or the perpendicular component of the wind. Then you have the tangential component UT. You have the axial induction factor A, radial distance from the axis of rotation R, relative velocity UR, angular velocity omega, then angle of attack, relative wind angle, pitch angle, and then the whole derivation starts. Based on certain assumption, and which is quite obvious because this is an simplified model. So this would definitely include some assumptions. So as listed out here, the UT would be much higher than UP. That means the tangential component of the wind is much higher than the axial component. Lift curve is linear, so that CL could be integrated as the CL alpha into alpha. Then the alpha is small. We have small angle approximations so that we could use that. There is no weak rotation. Blade has constant twist. No twist and constant chord. But yes, this model can be extended further to incorporate the blade twist or non-uniform chord, those things. So with this assumption, we are going to derive the linearized model. So what we have now, axial flow. Once we take the, considering the assumption about lift curve, which is says that the lift curve is linear, then we can write L bar up rho C CL UR square up rho C CL alpha UR square into alpha. Now we use small angle approximation, that is tan inverse of angle would be that angle. So what we have is that alpha is P minus theta P, which is tan inverse UP by UT minus theta P. We can write UP by UT minus theta P. Therefore, what we get L half rho C CL alpha UR square into UP by UT minus theta P. Now, if you recall, UR square is UP square plus UT square, which is again UT square, because we use that approximation that UT is higher than. So this approximation allows us to use this. Then we can write this would be half of rho C CL alpha UT square UP by UT minus theta P. Half of rho C CL alpha UP into UT minus theta P UT square. So this is what we get. Okay. Now what we have for flapping blade, uh, tangential velocity, as usual, the radial position multiplied by the angular speed, which is actually the tangential velocity, which is ut, is actually reduced by the cosine of flapping angle. However, due to small angle approximation, this is ignored. But usually what happens is that the tangential velocity gets reduced by, so now since that is ignored due to small angle approximation, that is ignored. Thus, we can have ut is omega into r. The and what we have, the perpendicular, the axial component up is u into 1 minus a minus r beta dot, because this is the reduction due to flapping velocity, that is r beta dot. So u is the free stream velocity here. So there are other factors such as yaw error, crosswind, vertical wind, wind shear, etc. That will also affect the wind actually experienced by the blade. Okay. So this can be accounted as perturbation on the main flow. Obviously, these perturbations are, these perturbations are assumed to be small compared to the axial wind speed. So we'll refer here as deltas. in our discussion. So these are other factors which are also affecting this main flow. Okay, and there would be impact, and that can be considered as. So what we can do, so now we say that we crosswind and yaw error. So crosswind, which is V naught, that is perpendicular to the axis of rotor. So this is perpendicular to the axis of rotor and parallel to ground. So this crosswind, this arises due to yaw error. There could be, this yaw error could be due to some misalignment of the rotor axis and the wind, or a so this could be uh, sudden change in wind direction or misalignment of the rotor axis and the wind. So this yaw error could come from all this. So what it does, this crosswind tends to increase the um, tangential velocity at the advancing blade and decrease it at retreating blade. So this different factors, which are this crosswind, these things, um, obviously arises primarily due to the yaw error, and the yaw error could come for sudden change in the wind direction or misalignment of the rotor axis and the wind. And so what happens that this crosswind tends to increase tangential velocity at the advancing blade and decrease it at the retreating blade. So we have already defined the crosswind from left to right in one of the earlier figure or diagram. So considering that, we would take into account this effect. So we'll derive that in the next session.